Okay, thank you very much for taking time of your evening to attend the IEEE Vehicle Technology Society Chicago Chapter webinar. Hope your evening is going well, and thank you for joining this evening. So my name is Alvin Chen. I am the chair of the IEEE VTS Chicago Chapter. And this evening we have Ted Bohn from the Argonne National Lab, who will be talking about vehicle charging systems from kilowatts to megawatts for anything that rolls, flies, or floats. So just a little bit of some particular kind of housekeeping rules. So we will have the talk from Ted, and then we will have questions and answers after that. So if you have any Q&A, you can enter in the Q&A section of the Zoom client you have. Also, as well, like I said, this recording, this webinar is being recorded, so you will get a link to this recording, which we'll be putting on our YouTube channel, and also as well a link to the slides, and also as well, if you need a professional development hour certificate or so to show that you attended this particular webinar, that will also be provided as well, where you can go ahead and you can enter your name there so if you need to have it. All right, so if you're not familiar with the VTS Chicago chapter, basically we are the chapter of the IEEE Vehicle Technology Society. So IEEE has many different types of societies. One of them is called VTS, and we are the VTS Chicago chapter. And we have our website, which is at IEEEchicago.org/VT. So you can see what our previous talks and webinars were about. If you're interested about the parent, the VTS Society, you can go to vtsociety.org. So like I said earlier, I am the chair. My day job is working for BMW as an AI and emerging technology researcher. And our vice chair is Kevin Sudenberg, who's here in the webinar. He's also from Argonne National Lab, same as Ted. And then we also have our VTS Young Professionals VTS Student Chair, 010 from IIT, and I don't think he's on this evening. And our mission for the VTS Chicago chapter is basically, we want to create a community of academics and professionals that are interested in all things about technology and engineering in the vehicle. So basically, the topics that we have discussed in the past have included vehicle ad hoc networks, 5G and connected vehicles, autonomous connected electric vehicles, vehicle network, the cloud, how to connect the vehicle to the cloud, connected vehicle platforms, smart cities, power charging, and etc. If you want to become a VTS member, you can go to this website there. A copy of these introduction slides will be provided after this, so you don't have to copy all that. And of course, if you want to follow us on social media, we have Facebook, LinkedIn. You can follow us on Twitter, and like I said earlier, our YouTube channel, where you can also see our previous meetings and webinars. One of the things with VTS is that we have a Vehicular Technology Conference that actually happens 2 times a year. The one that's happening in the spring is actually in June of this year, and it's actually going to be in person after 2 years of being virtual. It's going to be in Helsinki, Finland. The cover papers has already passed, but if you want to register and attend, you can do so at that URL. And then there's also a fall version of the Vehicle Technology Conference. That hasn't been announced yet, but it should be announced pretty soon. Actually, the VTC Fall Conference was actually 2018 in Chicago. So hopefully, I think this year it will probably be back in person again, and actually might be a hybrid. All right, so we're going to have Ted Bohn, who's going to be our speaker, and I will ask Kevin to introduce him. So Kevin, go ahead.
Thanks much for the intro, Alvin. I'll let Ted go into much more detail. His credentials are very long, and he has had an immense amount of experience as a principal engineer here at Argonne, developing standards from everything from what the standard plug, the J1772 plug, that if anybody has an EV that you use to charge, you can thank Ted for having a part of that in his historical efforts in developing charging, both for light duty, medium duty, and heavy duty vehicles at Argonne. So he's got a total of 35 years of advanced technology and alternative energy fueled vehicle research on the vehicle system side, as well as mainly on the grid side. And he's really just a wealth of information. So thanks a lot for joining us and providing this presentation today, Ted. I guess I'll hand it over to you.
All right, thank you, Kevin. So let me just stop sharing. And then Ted, you can go ahead and share. And like I said earlier, if you have any questions for Ted, please type them in the Q&A, and we will address it after Ted finishes his talk. All right.
Okay. Yeah.
All yours, Ted.
Thank you. So again, I'm Ted Bohn. My contact information is up there. If anything interests you, you can follow up an email to either Kevin or myself. And we have a monthly industry integration, industry engagement meeting that most of these slides are from those meetings. So if you like what you see here, we meet once a month and we talk as an industry, and we have 600 people in the distribution list, and we usually get about 100 people attending each month. So that's the context of this. I'm going to just turn off my camera because I don't think it adds anything to the presentation. Let's see. And I'm going to look up at my other, the main, so okay, so it sees that. So can you confirm that you see my screen?
Yep, we sure can.
Okay, good. So anyway, so like I said, it makes it easier for me to look up at my bigger monitor. So today we're going to talk about everything that rolls, flies, or floats. I'm going to go through fairly briskly. We're not going to get into the station architectures, but at the end, we're going to show a lot of how expensive and where the costs lie, in addition to the technical specifications. So technical specifications and historical parts first, then into, what are we doing? So this is a rendering from ABB, who basically said we're going to have these things with awnings. We're going to have depots that have overhead gantries that basically have long truss structures that drop down the connectors between the vehicles. And then we'll have other ones that are more typical, like a pump for smaller. So basically small, medium, large. So with that, come on. So today we're going to talk a little bit about what we do at Argonne Lab, talk about, history from 100 years ago, 30 years ago to today, talk about the history of charging from, AC, DC wireless. Then we're going to talk about connectors from 3 kilowatt to, 3 megawatt. And then we'll talk a little bit about DC as a service and other things, but I don't think we're going to get much into the grid side of things. So just kind of high level, this is the building on site at Argonne Lab called the Smart Charging Plaza. And so otherwise known as the Interoperability Center. And so we study a lot of different aspects of interoperability. So you can see they have solar canopies, EV charging, and then this is a representation of what's inside and outside the building. So inside we have parallel busways with 480 volt non-islanded power, and then we have the islanded switch. So we have a microgrid with lots of AC and DC sources that are interacting, and then grid emulators and vehicle emulators. Outside, we have a 1 megawatt, 500 kilowatt hour grid storage unit connected to an 2 MVA transformer, and then we have a megawatt of charging stations. So looking at it from the other side, it looks like this. So we have the medium voltage connection. We have the 2 MVA transformer. We have the load center with a whole bunch of spare circuits for other experiments we run here. We have the grid storage unit, which looks like this before the batteries were installed. So this is the area where the batteries go. This is the power electronics that ties the batteries to the grid. And this is the HVAC system that keeps the climate control steady. That's basically tied in parallel with the grid feed. So we can actually open the contacts to the grid and island the entire facility with the grid storage and the photovoltaics. So here you can see a different perspective, 1, 2, 3, 4, 200 kilowatt cabinets, and then a fifth one out front for 1 megawatt of charging, and then some of the vehicles that we study. So going back, running the calendar back 60 years. So 60 years ago, GM built a bunch of exploratory vehicles that are in the GM Heritage Museum right now. So you can actually go and see and touch these cars, and sometimes they open the hood. But what's under the hood are a lot of silver zinc batteries. But what's interesting, as much as people thought that this was new, they had 532 volt systems back then. So not really talking about architectures today, but typical vehicles in the last 10 years have been 400 volts or less. In the last 3 years, they've gone to 6, 7, 800 volts, and now with the Lucid, 900 volts. So you can see how it's creeping up. But 60 years ago, 532 volts was a good voltage, and you can see how tough it was using all discrete devices and analog controls. So no such thing as a microprocessor 60 years ago in a vehicle. So going back just 30 years ago, and that's one of the projects I worked on at GM was the EV1. So the first generation had lead acid batteries, and it had 1,300 pounds of batteries in. Compared to the Hummer, right? So you said 1,300 pounds, oh my goodness, that's a lot of batteries. Well, it turns out the Hummer has 3,000 pounds of batteries. So the entire EV1 with lead acid batteries is underneath the Hummer today. So that's how much more batteries people are putting into electric vehicles than they did 30 years ago. And again, significantly more money. Although because of the advanced technology, the bonded aluminum and all the different things, they estimate that the real price of the EV1 would have been $100,000 back then as well. Second generation had nickel metal hydride batteries. You can see that it was a lighter car, even though it had more energy. And then of course, moving forward to today, we have lots of vehicles with lots of lithium ion batteries, of lithium iron phosphate, cobalt anodes, many different chemistries, many different cell of the 4680, the 68 68 series, and all the different blade batteries. We're not going to go into that today, but suffice it to say, from where we were to where we are in the last 10 years, a lot of models of vehicles are available today. Some can push over 400 miles range. And of course, fast charging. So looking at the Mach-E and the Lucid, and some of the Tesla vehicles are pushing well over 250, 350 kilowatt for a light duty vehicle. Moving into medium duty, we have a lot of talk about the Rivian delivery vehicle, the Bright Drop, the Freightliner, and Ford delivery chassis, along with the Silverado and F-150. So again, lots of different charging powers for medium-sized vehicles. Back of the envelope, just something to remember from today's discussion about anything that rolls, flies, or floats, and things that are from kilowatts to megawatts. Usually you charge this vehicle somewhere in the sub 200 kilowatt range. Again, if you had a 200 kilowatt hour battery, then you would charge at 1C would be 200 kilowatt if you can get that done in 1 hour. If you want to go faster than that, if you want to go in 20 minutes, you have to do 3 times that, so about 600 kilowatt. So, but the consumption as you drive this vehicle, you say, how much do I have to put back in after driving a shift? It's about 1,000 watt-hours per mile. And that's kind of a nice round, even number for a chassis this size. So again, if you have 100 miles to go and you can charge it at 100 kilowatt, it's 1 hour, right? That kind of easy math. Bigger vehicles, of course, use more more power, and you can see how they have batteries on the side, batteries behind the cab, batteries underneath, batteries on the side. So you can see very similar, architectures, and we'll get a little bit more into that on the next slides. But these use about 2 kilowatt hour per mile. And if you have 400 miles range at 2 kilowatt hour per mile, it means you have to put back 800 kilowatt hour. If you do that in 30 minutes, that's a 2C rate, or 1.6 megawatt. So whenever we're talking about this megawatt plus charging, this is why. A vehicle this size to replace 400 miles of range in half an hour requires about 1.6 megawatt. So again, just back of the envelope, 2 kilowatt hour per mile, 400 miles, 800 kilowatt hour times 2, 1.6 megawatt. And again, just going back to if you have 8 hours, then it only takes 100 kilowatt for 8 hours to get 800 kilowatt hours. So you don't have to charge at a megawatt if you have time. But if this truck has to go back out in the time it takes to take a bathroom break and hook up a new load, right? That's what some businesses are. And then the question is, well, that's for one. What if I have 100? And instead 100 is nothing. So this site, this Google photo shows 2 sites at 600 spots each. There are 1,200 trucks, or spots for 1,200 trucks in these 2 places off of the San Bernardino Freeway in Ontario, California. So that's going to be a challenge in the future on, you wouldn't do a megawatt times 1,200, because that would be, again, more than 1.21 gigawatts. But it is, or that would actually be exactly 1.21 gigawatts. So that's an interesting, if all of these want to charge at a megawatt at a time, it would be gigawatts. So going back to what's under the hood. So this is a rendering of you'll see more physical pictures, but this is just ones I grabbed. These are old slides, just to be honest. from when the truck was announced back in 2017. So you just see bricks of batteries underneath the cab. You see what looks like 1, 2, 3, 4 Tesla Model 3 motors, and that's pretty much what they are. We'll show in the next image of what they look like in not as a computer rendering. And then the inlet. We're going to talk a lot about the inlet today, or basically what you plug in here. So this is just, again, a computer rendering with the highlighted motors where you have one motor per wheel, so you can do very good traction control and anti-jackknife and all the different things you can do. And of course, the acceleration rate of having that much torque of having one motor per wheel with a single gear ratio. So this is what it actually looks like in person when you say, oh, look at that, air hoses and hydraulic lines. Yes, air hoses, hydraulic lines, and of course power and sensor leads. So again, 1, 2, 3, 4 motors, but a very robust axle assembly. So you can see how maintenance would be as straightforward as it is on a conventional truck today as far as reaching things. Talking about how the power gets from the grid to the vehicle, this is an illustration of, we have transmission line towers at about 69 kV. We have distribution ones that can be somewhere around 13 to 49 kV that go down to our low voltage transformer, right? That has 480 volts goes into here. So on the red is a low voltage, which goes into the charging station electronics and comes out as DC underground into the dispenser, and then from the cable into the battery. So that's basically the nuts and bolts of how trucks are charged today. And this is at the Southern Cal Edison facility. So going back to everything that rolls, flies, or floats, there's a lot of applications. If anybody watched 60 Minutes on Sunday, there was a story where the reporter actually flew in an eVTOL. So all about where eVTOLs are at, how soon they're coming, all the different vertiports and other access. So again, not coming soon here, and FAA certification probably within the next year to two. And again, a lot of it can carry packages without humans right now, right? So as always, it's one thing on safety for humans, is another thing just to carry things. Mining equipment. So we have tethered mining equipment today, and in the future we'll have battery electric mining equipment. And as you know, the mining equipment never wants to stop. The machine shouldn't. The operator can be switched, and the machine should keep going. So again, if it's not moving, it's not making money. We have boats. So this is a marine example of, boats don't have wheel chocks. So when you put this cable in there, the boat floats around, and of course you have to have cord handling and other different things. This is a ferry in Bangkok, doesn't use one, but uses 26 inlets. So in order to instead have one big plug, they have 26 average size plugs. And you'll see the Mcs connector will actually replace all 26 with one plug. This is interesting. There was one used in my neighborhood the other day where there's a very small arborist, or basically a high lift that folds up and can drive through a 4-foot opening down your sidewalk between the houses, and then goes up 60 feet and has attachments for electric drive, and we'll look more at electric tractors later. So again, rolls, flies, or floats. Going back 100 years ago, and you can see this is an ad. It's a magazine ad for Edison batteries that basically say lead acid batteries aren't as good. And this is, a note from Steinmetz to Edison, basically saying, we experts think that this is a good battery, but stating that you can't afford to feed a horse. A horse is really expensive, but battery electric vehicles, they're affordable. So that was 100 years ago, 1914, or 108 years ago. And the same thing goes about DC chargers. So this one is called the Watt station. Turns out the one 100 years ago is also called the Watt station. This is a 6 kilowatt DC charge station, and that light isn't a bad print. There's actually a mercury vapor arc rectifier behind there. So before solid state devices, there were vacuum tubes filled with basically a mercury filled arc tube that would rectify the AC into DC with a rheostat and a plug that you'll see on the next page. So again, 8,000 of these were in use basically 112 years ago. The same thing goes about billing systems. They had pay meters. Basically, you would put a coin into the meter, right? Much like a parking meter, but this one dispensed electricity. So you would put a certain number of coins, you get a certain number of kilowatt hours, and it would turn off the charge station. So this, in fact, is a 150 amp DC charge station from 108 years ago. And this was put into in Cincinnati, Ohio. So again, these are just old articles, but things that existed that people say, oh, we need more charging infrastructure. There was, and it kind of looked like a parking meter. And again, the rheostat and all the different ways that you adjust the current, but 100 years ago. So going back just 50 years ago, there were 30 EV manufacturers. So much as say, oh, there's 30 manufacturers now. It's like, well, to be honest, they were small and old. Again, the AMC Jeep was not the fastest, but again, mail delivery Jeeps didn't have to go fast. But there were 350 of them built. So they're built right here where I am, well, right here in the Chicago area, and in 1974. So again, what they're about to do with the Oshkosh order, they did a long time ago, and about the same type of question of, can we afford it? Is it worth it? Also battery swapping. So battery swapping in the United States hasn't taken off, but in Asia and other countries, that's a model where you lease the battery and you basically just pull it in 2 minutes. You can swap it out basically as fast as you can fill a car. And so Tesla did a demo, but of course they didn't pursue it because the cost of the battery swap was more than the cost of the electricity. And so people felt that it was okay to wait. Same thing goes with mail carriers in the 1970s. And then of course, here's an example of the 1930s, the FedEx, not FedEx, UPS trucks charging on this 150 amp DC plug in the 1930s. So basically just under 100 years ago. And then some of the vehicles from the 90s. So going back to this connector, so there's a 150 amp connector, very similar to what we have today. This is a coaxial one, so the center pin is live. The outside part is the ground. It was 48 volts because that was the size of the lead acid batteries, and 150 amps. And so that was, 30,000 of them were in operation 108 years ago. 109. So in the 1990s, we had the first version of the J1772 plug, and we had on the EV1 and the S10 inductive couplers called J1773, which again was abandoned when they decided to go to a conductive standard in California and eliminate the inductive standard. And then in the 2010 era, we created this 5-pin version that goes up to 80 amps at 240 volts or 19.2 kilowatt. And that's what most cars use today for AC charging. We have wireless charging. The SAE J2954 standard has a resonant coupling between the pad and the vehicle, and I guess Hyundai is supposed to come out with this next model year, but again, it's been a long time. So the gradient, there are overlapping power levels. So you can have level 1 AC, which is 120 volts at 20 amps, which is what you get out of your wall for your hair dryer or your fridge in your garage, or the welding plug, right, which is somewhere between 16 and 80 amps at 240 volts. So you can just see the cords get continuously bigger. And then for the DC level 1, which there are very few, runs the 80 amp contacts in here with DC on them. And the level 2 DC runs at the time of this slide was 200 amps, and now with liquid cooling 500 amps. And the same at the time of this slide, 8 years ago, it was 500 volts, and now it's 1,000 volts. So this connector, liquid cooled with these 10 millimeter pins, or 8 millimeter pins, sorry, can push half a megawatt. And that's what we start on going on to the CCS. So CCS to MCS. So the new GBT is also called ChowG, so they want to be the same as CCS. So much as this connector can go 500 amps, they want to go 600 amps. And so it's specmanship. And so this goes 1,000 volts. This one wants to go 1,500 volts. Unfortunately, it only takes you to 900 kilowatt. And that's not enough to charge a semi. A medium-sized truck, yes, but not a semi. So GBT/ChowG is still, a work in progress. Uses CAN communication versus power line communication. So similarities and differences on the Chinese GBT 20234-3.3 connector standard. So this is how the Chinese DC vehicles are charged. You'll see this connector in other slides later. And then the CHAdeMO standard is being phased out, which there are a lot in parallel with the CCS and CHAdeMO. And then the Tesla vehicle charging standard, which runs up to 250 kilowatt today. Allegedly later this year, they're going to push it over 300, like 360 kilowatt, which means 900 amps. They're going to push through that pin, which is a lot of current. So as you can imagine, it's not going to push 900 amps for long, but it'll push it for a while. So stating the obvious, we start with small vehicles, small charger, the AC and AC Tesla and SAE connectors for up to 19.2 kilowatt. Moving up to the 3-phase 480 volt and DC versions, you can push up to 320 kilowatt, which is what the Tesla vehicles use in Europe and some places in Asia. And then the CCS connector we just talked about that goes up to 500 kilowatt. Pantographs on buses, the SAJ3105, there are 3 variants, ones that the pantograph goes up, one that the pantograph comes down like this, and ones that have a telescoping probe that comes from the side. And now the SAJ3271 connector, that'll go up to 350 kilowatt. So again, 3,000 amps at, starts at 350 kilowatt, 3,000 amps at 1,500 volts or 4.5 megawatt peak. So the history of this group was formed as an industry consortium back in 2018. Here's the history of how we got to be where we are. It used to be called the HPCCB, and some people thought that was a bit long. But most of you who work for a German company realize that they don't really care about extra letters, versus here we like TLAs. And so after the down select from the that came out with the version 1 connector, it was shortened to Megawatt Charging System, or MCS. So the version 1 had this triangular shape. This is taken from the patent. I know it's a little bit thin, but that's the best image I could get. That's public domain. And the same with this rendering. So because the Charin group is members only, I can't share any of the drawings from Charin, but I can share things that are on Wikipedia and in the patent office. So it has round pins, the interlock and the earth pin in a triangular shape with a locking pawl. The fingerproofing, you could actually get your finger probe in there and it would not pass the UL 2251 test. So they abandoned this one and moved on to flat pins. So this is a very tall one with 2-inch contacts, basically a lot of copper, and then something that looks like a hairpin that snaps over a bus bar with the earth and the pilot and then prox communication pins. This one hit a dead end on IP issues with TE Connect, and basically would not withdraw from their patent claims. And so they had to abandon that and move on to V3.2, which is going to be released soon. So at the EVS 35 event, there'll be a big press release. And so at the end of 2021, it was pencils down. They said, we're done changing it. Now we're just going to refine. And so similar thing, but much bigger pins, and you'll see it on the next slide. In fact, here it is. So this is as close as I can show of the physical connector until EVS 35, but this was on the LinkedIn. So this image here with the text, I basically just grayed out the text and put some dots on there. So there are 20 millimeter power pins pushing 3000 amps liquid cooled. There are 8 millimeter narrow connectors we're going to try. We are investigating using 10 base T1L or T1S, I think it is for automotive. And then the proximity and interlock pins, along with a 12-volt aux function that can wake up systems. And that's what I'm working on this week. For basically when you have a black start and you have a vehicle that's sitting in 40 below weather and it will not wake up because it hasn't been charged, this will give enough power to wake up the system, close the main contactors. And once you have the main power, you kind of bootstrap. Same thing goes if you have infrastructure that's been, cobwebs for a long time and you have a flood, a fire, whatever it is, and you haven't woken it up in years, like with regular internal combustion generators. That day you really need it. You don't want to go find some jumper cables or a file or whatever it takes to get it to go. You just want to plug it in and have it wake itself up. So that's what that extra pin does. This is the size of the connector on the V2.4, and there will be similar handle. So this cable here was tested at 1000 amps with this diameter of conductor and liquid cooling. So that's kind of the thrust of what we're going to talk about today. So this goes back to the Chowji connector, which has the connection detection pins. It has, theoretically can possibly power line communication. There's still a work in progress, and I'm not sure they're going to explore Ethernet, but within 3271, we are going to try to put all 3 physical layers on there so that different industries can choose which one they want. This is just a dimension of the CCS coupler, which is 66 millimeters wide. The other one is 105 millimeters wide. So you can see it's 20 millimeters wider on each side. And so it just kind of looks like mouse ears. So when you hold this connector up to this connector, it looks like the same thing. It is shorter with 2 little bumps on the side. So just to, if you use a CCS connector, it's almost the same size, but it moves from, 350 amps to 3000 amps. So moving along about adapters and multiple output cables, this is an example of the Tesla stations in China that use the Chinese GBT standard. So it basically has this style of the CCS coupler and of the other one and of the GBT 20234.3 connector. So you can see how it's just kind of a mess. You have this one or this one, depending on which cables are on there. So much like the unleaded and diesel, you're going to have things that are legacy for legacy things. For MCS, we don't have any legacy stuff. There's not AC and DC. There's just a clean sheet. And that's what I'm the chair of that standard. So here's an adapter that goes between these 2 standards. There's an adapter for that. And again, this is the whole, red X. We don't want to have to adapters, but that's what Tesla had to do. So moving along, and again, any questions, just put them in the chat box. We'll get to them later. SAJ 3271 and AIR 7357 for the aircraft charging standard rely on the IEEE P2030.13 functional specification standard for DC as a service. This DC as a service presumes that the utility will own not only the medium voltage connection, not only the low voltage transformer, but the power conversion equipment, the solar, the storage, and the distribution up to the vehicle, and will sell DC as a service at the point of use. So the line of demarcation isn't here, it's here. And that's where the point of interconnection and things that we're probably not going to get to today, but there is a business model of DC as a service. So 3271 covers the utility interconnection, the power conversion into a form that can be used by the vehicle in high power, high current DC. So again, if we have shared vehicle service out, we're looking at something like 10,000 amps at 1500 volts for distribution. And then each of the taps can take off, up to a megawatt each or multiple megawatts for bigger vehicles. So that's where the whole idea of the multi-port, kilowatts to megawatts with DC distribution. So 3271 is structured in 5 volumes. The technical information reference is the first stop on a SAE standard. It goes from information reference to recommended practice, which is the could to the should, and then the industry standard becomes a shall. So again, could, should, and shall, we're working on the could. So we're writing down, we meet weekly. If anybody's interested in joining the standard, you can contact me. I'm the chair, and we've been pushing very hard since the end of last year when I got permission to launch the standard. We want to get this information reference out now, which will be about 5 years ahead of the European standards, because they take many, many years to iterate and add annexes and resolve things, versus we can move much quicker with this TAR, RP, and IS version. So volume 1 covers just the electromechanical side. And much like a chapter, you don't want to read 1,000 pages per chapter. You want to break it into 20 or 50 page bite-sized pieces. So the electromechanical standard is going to be harmonized with the IEC 63379 mechanical specifications on how that coupler is drawn, how the cooling works, the reference devices for testing it, limitations, touch safety, all the things that have to do with electromechanical part of the coupler. The layer part 2 is the physical layer, as I talked about CAN, PLC, cybersecurity, just anything that has to do with software security. And then of course the physical interlocks, where you never ever want that connector to be unlatched while it's pushing power. Because again, a 3,000 amp interrupted 1500 volt circuit will make one big fireball. So I'm in charge of some of the fault mode testing. So we're doing fault testing up to 75,000 amps on short circuit testing to make sure that the connector from the Lorentz forces, you can imagine, will be immense at 3,000 amps with cables that are adjacent to each other, even more so at 70,000 amps. So those are some of the mechanical things we have to do along, and where the physical connection detection circuits are really important for human safety. Because again, in the past, there's no such thing as anything a human could touch that would go to a megawatt. Even 500 kilowatts today, half a megawatt, seems very odd, but yet it's safe, and millions of sessions are done every day like that. Not every day, but sessions are done every day up to the millions over history. DER, this is where P2030.13 comes in on anything that's a microgrid, anything that has to do with a grid service, B2G, all of that fits into that chapter. And then of course, validation testing, interoperability, and other testing requirements on reference devices. So what do you use as a golden device to show that something can be type approved or certified as in interoperable between combinations of chargers and vehicles. So that's the 3271 standard. So this I thought I would put in here because this is the business side of things. It's not clear like a car that you have to buy the car. You can lease the car, you can rent the car, you can have the car as a service. There's many different ways you can get cars. The same thing goes with charging. So you can get the DC as a service where you buy the DC power at the point of use, and all the things upstream are owned by the utility. All the things downstream, just the distribution equipment, are owned by the facility owner or the fleet operator. Charging as a service actually takes the whole thing. It's all the equipment, it's all the billing, everything, and you basically just pay a monthly fee for the use of it. So a lot of the school systems are doing that, or municipalities where they don't have, $50 million to invest in something. So Schneider has Structure with an X, is their charging as a service, and basically they provide everything, and you just pay your leasing fee for the entire charging infrastructure and all the investments, the generators, the batteries, the microgrid, everything Schneider provides as a service. Energy as a service is the negotiated rates, and again, the whole energy services interface and the energy services billing. Again, the dial up, dial down, all these different things bundled, again, aggregators. So this would be the whole idea that energy as a service already has the demand charges bundled into it, and that the company who is offering the energy as a service mitigates those demand charges. So you don't have this unexpected $50,000, penalty, not penalty, but added demand fee on top of your energy fee. So that's where energy as a service comes in, and then the vehicle as a service where you don't even own the vehicle, you just subscribe. And so there's a company called Watt EV out of California. They have, I think, 60 trucks that they have purchased, and they have a facility in Bakersfield that can charge 60 vehicles fast charging. So they will offer vehicles as a service, including the charging. So many different ways to finance it. And again, CapEx is different than OpEx money, right? So that matters. One question is, how do I know what I'm getting out of the end of the pipe? And that's what I work on. So this turns out where I'm sitting is where this photo was taken, on benchmarking different meters. And this is some of the meters we developed at Argonne Lab. And so this is the previous generation. The new generation is about half this. So it's about 1 inch by 1.5 inch for 1500 volt, 3000 amp meter. So again, very small, very affordable, and again, traceable accuracy. So these are the different meters that we use for benchmarking. Another question is for field testing. How do I actually load up this thing? If I got to show that I can do, for instance, 0.5 megawatt, how would I do that, and how do I move it? So the solution that I've come up with at Argonne Lab is to have a whole bunch of 6 kilowatt loads in parallel. And so you can see these come on little racks, like a baker's rack, and they fit in the back of my truck or into a trailer, and they bundle the cables together and plug them into a chassis, and that chassis plugs into the station. So here's a representation of how I set it up in the field. So again, I can just pull up, stack everything down, plug in a gazillion cords, but that's how I load up 0.5 megawatt with this portable station that I can lift without a forklift. And that's very important to me because, again, the riggers, the tailgate fees, there's just a whole bunch of specialists that you don't need if you can have a modular load. So again, you can always rent a load, but this is another way to do it. So going back to charging plazas, and I'm trying to remember if we're going for 6:45, when should we wrap up?
Yeah, we can go to about 6:45 or so, yeah.
Okay, so about 7 more minutes, and I think we can get to most of the things. So these plazas, the Bakersfield one, this one is in Portland. So there are 2.5 MVA transformers that feed 5 megawatt into this, into the load centers. The load centers are connected to the power conversion equipment. This open spot where the yellow boxes will have secondary, second life batteries and peak energy storage, like that container of batteries we showed in the opening slide. That would go here to do the peak shaving. And then there are removable plates where they can actually reconfigure this and use this as a test bed. So it's very similar to what we do at Argonne Lab. And so each of these stations can be unbolted. These plates actually come up and they can swap out charge stations. So an MCS station is going to be put in this open spot here. So you can see there are 4 islands. This is outside the Daimler truck facility. It's co-owned by Daimler and PGE in Portland. So this is the electric island that was deployed, I think, in 2020. So moving on to other deployments, Tesla has been deploying some of their MCS systems both in Nevada and Modesto, California. So this is a photo of the mountains outside the factory in Reno. So you know for sure that 4 trucks exist, or there's a very good rendering of 4 trucks parked, and you can see the islands, and we'll see what the rest of the facility looks like, the isolation transformers, and then the power converters. So these are intentionally vague and blurry, but there's the MCS connector that Tesla has built. It's called the V2.1. The earlier version that was tied up in the patent IP is what they're running. But basically, the connector was tested last year or the year before last. Is what they're running on these trucks, and yet to be seen what they use for the rest of the fleet. But either way, you can see the station's about 7 feet tall, just judging from the size, the height of the mirrors. These are about 7 feet high. You can see the cord is less than 10 feet, maybe 8 feet from the dispenser to the truck. And again, liquid cooled heat exchangers inside of here. Again, fuzzy photos. These are just from Twitter, but this is the output where the cable goes out, judging from the width of the cabinet to the width of the cable. These are about 2-inch diameter cables. And then this is just again, a blown up fuzzy thing of that connector we saw with the Hershey bar kind of contacts inside. And again, I don't have any closer public domain photos. These are as close as I get. So cable distances are going to be important, especially for aircraft. So we talk about rolls, flies, or floats. Here's the flies part. So this is a computer rendering of Lilium, is a company in Germany working with ABB. You can see how there's a telescoping pole. So I would guess that this part slides in and out. There's a caster, and then of course there's some kind of computer rendering of a flexible link that plugs into the quote unquote fuel tank. So the AIR 7357 standard, which I'm also the chair of, covers that. And then in 3271 /3, we're going to talk about cables and cord handling systems. So you can just visualize, like, this is not easy on a thing that's got big wings and spinning props. You can't have your charge station next to it. Kitty Hawk has a kind of a more rugged facility, so you can see they have a solar panel and out in the patch of weeds, and then they just got a box laying on the ground. So it's like, okay, that's what we're doing today, but that is not going to cut it for the future. So going back to the Modesto installation, this is the transformer pad before the transformer is installed. This is a Megapack, a Tesla 3 megawatt peak shaving unit, an ISO container, which I would assume has instrumentation and switchgear in it. We have an isolation transformer before each of the AC to DC power converters. And then since there are 8 converters and 4 dispensers, I would assume that it's 2 dispensers each. And just seeing the photos that there are 7 70 kVA power converters in here. These are about 500 kilowatt output each, or a megawatt for a pair of these. So that's how that one is done. This is the looking at it from the other view of the isolation transformers, power converters, and then the foundation for the dispensers and where the dispenser will be. So this is the site in Nevada, just to show how much you have to dig out. So normally you dig a hole or a pit or a trench. This one is like the size of an Olympic swimming pool. It's a huge excavation for all those conduits. So again, these are the 2 pair of 2.5 MVA transformers, which is a typical limit of 4,000 amps on a 480 volt transformer. The switchgear that the circuit protection, the rows of isolation transformers, and then the output power converters that go out to the dispensers. This is what it looks like with the concrete poured, transformers, switchgear, isolation transformers, and then the row of power converters and the dispensers. So going on to everything that rolls, flies, or floats to round out this talk, John Deere has been doing swarms of tractors. So they have one master tractor. This one has a 1 megawatt power wire on a big cord on a reel. And so it drives back and forth up and down the field, keeping track of where it left the cord. Then it has swarms of tractors that are tethered to it behind. And so this is what John Deere last year. This is what they showed this year, 1 megawatt hour, 1 megawatt hour on wheels on a tractor that has no driver. Now the driver is optional, where they can attach this cab unit that has no mechanical connections. It's an office pod that connects to it. And again, 1 megawatt hour, 500 kilowatt drive system, all autonomous. How do you charge it? With this fire hose of a cable. So these are Staubli 1000 amp bayonet connectors, and again, just like giant jumper cables, that's how they're charging this one. And it looks to be about a 700 volt system. And from this gauge, it was 230 amps is the rate they were charging that day. That's John Deere. Locomotives. So Wabtec has a locomotive with 7 megawatt hour batteries. So again, they get rid of the engine and the spinning machinery, and this whole red section is just full of batteries. The connector in this case is a 5-pole 480 volt 500 amp per contact Amphenol connector, and in the future we'll probably use MCS also. So again, big connector for plug-in locomotives. Going back to the racing side, so right now the FIA EGT series uses 2 350 kilowatt connectors with a merge box to basically charge in parallel to get it to go fast enough. So this is, I think, a computer rendering, but it shows the power output. It shows the percentage of basically how full the electric fuel tank is and how long it's been on charge. So again, that's racing. Then moving around the corner to aircraft, Joby has their different aircraft that has done 1,000 test flights, and they're expected to have passenger service in 2024. They have done their custom connector for now that fits inside the motor pods. And again, eventually I would guess they would use the AR7357 once it's certified for use. And again, just to point out the things of 200 miles an hour, 150 miles range. So eVTOLs are very close on running real flights today. We talk about rolls, flies, or floats. In marine racing, Mercury Marine is very serious about electrification, and again, they have very high-end, V12 engine-powered outboards, and they would have the same thing as the Tesla type acceleration for boats. And so here is a E1 race series hydrofoil. When again, if you watch hydrofoil racing, it's just the hydrofoils, the lifting surfaces, and the propeller are all it's in the water, and the rest of it is just made for speed. So, and then on the heavier side of marine, we have mooring clamps. So the ferry, when it pulls in, doesn't use a rope to tie it off. They have these big vacuum clamps that have a compliant coupling, because the boats are moving, the ferry is moving up and down as they're loading and offloading passengers and vehicles. As the ferry pulls in, the mooring clamps grab onto the ferry, the door opens, the cable telescopes out and drops in and latches in 20 seconds. So from coming to a stop to flowing power, 20 seconds, 4,400 amps flow through this cable. So that's in service today in electric ferries. And then this kind of just shows what's inside the charging stations today. So this is an RTM 75, a tritium 75 kilowatt charger. On the bottom is the heat exchanger with the fan, and again, a great big hole so it doesn't get stuck full of cobwebs or dandelion seeds. The AC connection, the fuses, and the circuit protection, the AC to DC conversion section, and then 25 kilowatt increments of DC to DC output for each of the outputs. So this is basically the future. Almost all stations will look like this. There'll be an AC conversion section and a DC output section, and then everything will be in increments of 50 to 100 to 150 as we showed before. And this is the same with the ABB, shows the things we had on the cover slide, which you'll have smaller systems that have power converter cabinets that have a dispenser, like the ones at Argonne Lab, to go, and that was in 2019. Last year they were doing 1,000 amp pilots, or basically megawatt in an ISO container. To this year they're running 3 megawatt in an ISO container. So with that, that's the end of our time. I just have more slides of things like that. Let's go back to questions.
All right, very good. Thank you, Ted, for that wonderful talk. We have about 10 minutes that we can do some Q&A. So Kevin, I see there's lots of questions in the chat and also some questions on the Q&A. So Kevin will moderate the Q&A. So Kevin, what do we have?
Sure. Thanks, Alvin. Thanks, Ted. That was great. I have sufficiently been able to geek out. On
well, it's
stuff.
nice that Kevin doesn't have to visualize this outside his door. So
yeah.
and to be fair, Kevin's testing a lot of the vehicles we showed in that thing. Kevin's run a lot of testing on that on the profiles.
Yeah, but this is I learned a ton. This is really interesting.
Again, it's different than what you're doing, right? So it's the whole thing. We're office mates, but we don't do the same thing.
Yep, exactly. Okay, moving into questions. And I guess to make note to everybody else, if you do have some specific questions, please put them in the Q&A section, and then it makes it a little easier to kind of work through them. So what were the reasons EV technology didn't develop popularize much earlier, given that it's been out there for several decades or a century, actually? What is different today, and are there newer obstacles EV technology is facing? It feels like EV development could have been on par with the electronic computers development today.
Right. And so there is this guy named Kettering, and he started this company called Delco, and he made it easier to start a car and drive it. And again, it was the infrastructure. So in the beginning, it was hard to get gasoline and it was easy to get electricity. That's why we had a lot of EVs. And then the opposite happened. We had the electric starter. We had engines that were reliable, that were electric start, and we had batteries that weren't light. And again, I have a whole bunch of stuff on that. So that's why we took a pause for chain drive and other luxury vehicles in the start of the last century. Why we had 30,000 vehicles, and then they fell out of disuse. And again, a lot of the electric trucks, the really heavy duty stuff, they had been used all the way into the 50s, right? So some of those trucks built in the 20s were used for 30, 40 years, and were very reliable as electric trucks, much as we have electric fork trucks. So the technology was just very good, but not as good as other things. And now we have the emission side, and of course battery technology, as Argonne and other people have developed anodes, as we saw in the EV1, right? Why don't we have a whole bunch of EV1s now? Well, that's why it's called the EV1 and not the EV1000, right? It was the first one. And so all that R&D that happened 30 years ago is reflected in all the GM and other vehicles. Like the Hummer is fantastic. That thing is 9,000 pounds, does 0 to 60 in 3 seconds, right? It's got marker lights on the cab because it is so huge that it has to have the 3 marker lights on the cab like a medium duty vehicle. So again, it's immense, but all that technology from the EV1 resulted in the Hummer. If you've ever seen or driven or seen the Hummer driven, it has some fantastic features. So anyway, but that was just it. It's been a process at Argonne Lab. We've been working on it many years. I've been working on this 30, 40 years, and it's a process. And again, right now we're seeing 50% increase in batteries. So in the last 10 years, batteries have been decreasing on watt hour, dollar per watt hour every year until this year. And now things have gone up 50% because of material shortages. So again, everything spikes once you hit a market limit. But before that, innovation kept bringing the price down, and that's why the Model Y was the most sold vehicle in California of all models, right? So it's fantastic to think that an electric car outsold everything else in that state. But again, subsidies and other things. So next question.
Great. Okay. Next question, I think that's interesting here. Would the grid have to be enhanced with larger wires or larger capacity in order to service a truck facility like the one you mentioned in Ontario, California, if each truck was an EV?
Yeah, so it's good that I parked on this one. So this is Johan Peters that we were on a conference panel last summer, and the big thing was don't. Let's see if there's an animation here. No animation. Anyway, so the main thing was don't blow the grid, right? Don't blow the fuse, right? So that's the main thing on a facility level. So these boxes, very indicative. So the facility stuff goes right here to the point of interconnection, and then of course the site optimization. So the Ontario, California one is going to be this. You're going to have other things in there and peak shaving, because again, you're going to have a certain amount of continuous average draw, and then the peak of when you turn things on and turn things off. So the overnight stuff, right, is the savior, because if you have 8 hours to schedule things, much like traffic flow, you can coordinate. If everybody tries to get through a corridor at once, you just have a traffic jam, or you have to build a 10-lane highway that's only jammed once a day, right? So that's the whole idea of the Ontario, California. So Ontario, California is actually the site of one of the RETA projects. And so they're going to be building probably 10 to 20 stalls there and learning from that to extrapolate. So again, you walk before you run. So, but again, no one has ever said we're going to do 1,200 sites and have enough electricity to do that. That would be hundreds of millions of dollars of upgrades to bring that much power there. So this slide is, kind of represents those rectangles, because again, there's always a price. It's not a matter of can you not do it. It'll just cost a lot of money, and then of course people say I can't afford to do it. So next question, Kevin.
Great summary. What is the efficiency of general efficiency of charging stations?
Yeah, so let's go back to, oh, here's another one. So it all depends on the architecture. So here is a company called Power Electronics SA out of Spain. And so Proterra has been licensing it. So they put everything on a giant skid. They put the medium voltage transformer inside. They have racks of the AC to DC conversions. And so each piece can be very efficient. And so this company called Imogen out of Milwaukee, they actually build their stuff in Chicago with a contract manufacturer. They're running at the 99% level. So a lot of these photovoltaics and the DC to DC converters can run at 99%. But you have cascaded things where you have the round trip efficiency. So the output converters, and that's what we were showing on. Well, that's what these are. So these modules, this one is actually AC to DC directly, but the other ones, are smaller power supplies. So this is kind of the new market. Instead of putting things in big cabinets like this, they can put things into small towers. So what used to be huge can fit into this thing that's roughly 3 feet square. And so the Terra 360 can run 360 kilowatt and run up to 4 outputs, having all 360 kilowatt on one plug, or 120 or whatever 90 kilowatt on each of the 4 simultaneously. So the efficiency is from the power conversion, and again can be as high as and that's where the silicon carbide and running these higher voltages that I keep talking about are getting there. So a lot of the internal buses are running much higher voltages to get your magnetic losses down. So again, just think about the PV industry and how far it's come in the last 10 years. The same thing goes with charging electrics. In fact, there can be a lot of the companies do the exact same thing of, Danfoss and Yaskawa and everybody. SunPower has a huge division that they're pushing into EV charging. So next question.
Thanks. Right. Will we ever see nuclear energy having a significant impact on EV technology in the case of submarines?
Yeah. So I'm trying to think if I have a nuclear slide in here. I'm just going to sneak ahead. These are old slides from other presentations, and we'll see if there's a nuke in here. So at Argonne Lab, we had a modular called MiFi, a modular reactor. I don't think I see it in here. So I'm going to say no, I didn't put it in there. So we studied it. I would have to say because of so the answer is, will we ever have the ability to? Yes. So that's what we're studying at Argonne Lab. They do design a lot of reactors. I had 2 years of funding to work on the truck step one. There's a video, produced by Argonne that shows what the architectural, and again, it's kind of a fenced-in area with a buried pit with thermal storage so that you can load average. So you basically store the extra thermal reaction energy in a molten salt, I think, and then they turn it into whatever the media is for making electricity. But the one part would be you would have to have an armed guard at each station because of terrorists, right? And so that would be the one that I don't think you could defend a station like that. You could build it technically, but I don't think you could defend it. So been proposed, and again, much cheaper than bringing the infrastructure, not much cheaper. It could be as cheap as building a new transmission line is to put a modular nuclear reactor in there, but defending and monitoring it, I think that expense is going to be hard to justify, especially with what's going on in Eastern Europe today. So next question.
Great. Do you think we will ever get to the point where charging will be as quick as filling up a gasoline vehicle like today?
Yeah, I think we're there. I think for some battery technologies, the question is at what cost. It's almost like the bedtime stories. It comes at a price. And so that's what Argonne and INL and others have been studying, is at what price. And so for anybody who's looked at or has a Tesla vehicle, they have a limit. They basically have a dossier or a passport that goes with that battery, and it sees how many times it's been pushed hard. And the more times you do it, the fewer times you're allowed to do it. So the answer is yes, you can push it hard. And that's in fact, what Tesla's going to be doing. They're going to be refueling a vehicle in 30 minutes, which is what a liquid fueled truck will take on the time it takes to stop and put the hose in there. But it's going to come at a price. You have heat losses, and of course you have wear and tear on the battery that you may or may not need if you would actually take an hour to charge versus 20 minutes.
Great. All right, I think we've got time for a few more questions here. Alvin, do you is it okay if we have a few more questions, or did you have?
Yeah. Actually, I see a lot of questions on the chat, so I don't know, Ted, if you have. If we go over 7 o'clock, if not, then we can, just try to do as many as we can. Are you okay, Ted, for continuing on? Or?
Oh, sure. Yeah. If you want to just cherry pick questions on Lucid.
Yeah.
So Lucid is pushing things at a 900 volt rate, so they can get that going. I didn't talk about automated connection systems, so we looked a little bit at the compliance systems with the marine stuff where it drops it into a pocket and it grabs it. We looked at the 3105, which has wide contact bars that have a lot of tolerance if the bus moves. So there's a company called Roxas out of Netherlands and Power Hydrant out of Boston. They have automated connection systems that they're working on that can see the vehicle, open the door, put it in the hole, and then of course allow the vehicle to move around. Because again, you wouldn't want to plug it in and have it snap it off if something moved. And like we're saying with the boat, ships doesn't have wheel chocks, right? Boats move around. Same with aircraft, they can move around, so you have to have compliance. So those are just some of the things on the bottleneck. And again, the battery itself, the solid state batteries, there's just a whole bunch of higher power density, higher energy density batteries that are going to have trade-offs. And so the thing I have on the screen right now is the peak shaving NextEra, right? They have a big project in California to put down these. So this is almost like the old days of a buffer tank for water pressure. Right, you basically just have local storage where you can let it rip. You can let a megawatt rip out of this thing and not perturb the grid. I think that's going to be the one of the important parts of this. And so, yeah. So I'm just going to keep going by and see if there's anything of interest that covers, Yeah. So these are the medium voltage side of things, the motor control center. So again, I hate to keep talking about the part that feeds. Today was mainly about how it feeds it. The battery itself is really a materials question. So that if you saw the Giga Texas Rodeo, that was just an awesome set of videos and with the drones and everything. But again, that 4680 cell is going to be a limit of how many cells can you produce, how can you get the heat out of the cells, But again, they went from 8,000 cells to like 600 cells by going to the 4680. So. And the same with the BYD blade. There's just a whole bunch of different geometries that allow things to charge faster. This is more on the medium voltage side. And we have, 13 kV that comes in. We have series cascaded converters that put out 1,000 volts or 1,500 volts DC. And we have more of these DC to DC converters. So this is one of the projects that Delta was funded from DOE, and this is what they actually built, right? So these aren't just, computer renderings. They built different sizes of electronics. And so these are being tested in Detroit at Next Energy. This is Eaton right here out of Milwaukee, and I think remember who the vendor was in Chicago. So the DC distribution center was built here in Chicago. And like I said, each of these phase converters are big, stacks of cells. And then the output are these 25 kilowatt bricks that are stacked into these dispensers that I talked about. So this is the architecture. But these are just different ways where getting a megawatt to a vehicle isn't really a challenge. It's more about economics and reliability and then safety, right?
And
So
I think that to tie things up here at the end, there's a couple of, we
Yep.
can almost vent a couple of questions together. So there's one, it's related to how big of a deal is EMI, EMC for EVs? And then also how, I think that kind of ties in maybe somewhat with another question, which is how feasible is wireless charging for EVs? What are some of the considerations there?
Yep.
I don't know if you want to hit on that real quick.
We can do that. This container shows what people have been showing is like, why do they keep putting them in these big metal boxes when these big metal boxes are so hard to hide? And the answer is because of EMI, right? I can have all my shielding. I can have my approach boundary. There's a whole bunch of reasons why a pre-wired system is better than the one we showed back here, where everything is spread out. I'll get back to it, right? Oh, and I'm gonna stop here on this one. So this busway system is going to be very important. So the wireless charging stuff, so the megawatt wireless charging is going to be a challenge because it's a lots of array. So each of the modules is about 100 kilowatt. So you need 10 receivers underneath a big vehicle to do a megawatt. So again, 100 kilowatt per vehicle, that's what's running in the Oslo taxi fleet. There's a bunch in the United States are running on buses. But this DC distribution, so this company called Shoals out of Nashville, and so they have this I think it's 750 MCM a wire, so big aluminum wire, and they can bond on these taps, and they can basically put a raceway. And this is an older drawing, so the new stuff is much more polished. But the idea is that you snap in different devices, including wireless, and so you would have one central power converter, and you have output converters that are laid into the pavement or wherever it's going to be. So it was very, very close to having this plug and play. Again, much like an outlet where you plug in a welder, but at the megawatt level. So that's what's going on. So I forget, there was another part. So it was wireless, something about power distribution. What was the other part of that question, Kevin?
Sure, sorry. The other part of the question is on wireless charging. How feasible do you think it is?
Yeah, it's here today. So again, the 2847 that we, I'll get it right. 2954/1 is the light duty, and 2954/2 is heavy duty. And so again, the heavy duty has different WPT classes. So 1 through 4 goes from 3 kilowatt to 22 kilowatt. And then level 5 through level 8 goes from 60 kilowatt to 580 kilowatt. So that's being deployed on buses and trucks now. There's a loop runs from Seattle to Portland on a DOE project, so that's running for the last year. So again, it's not coming; it's here. It's just kind of pricey. But those trucks on the time the truck is reloaded, it's ready to turn around and go back to Seattle. That kind of thing.
Great. I think maybe we're over time here, so we'll go for one last question here. In general, why is battery swapping not considered?
It is. It's the ownership model that is the biggest part. So I can give you a great anecdote since everybody loves a good story. Project Better Place spent $800 million. I don't remember if it was $1 billion, but it was a lot. And in the end, what sunk them wasn't the battery swapping. So there are a bunch of, I can't remember the names of the companies. There's a couple of US companies have stations that they're going to be deploying here. And again, you can kind of unload the station out of a truck, much like putting together a car wash. If you don't have to have water and drains and stuff like that, doesn't take that long to build a car wash. But these swapping stations have to have other batteries on charge. So in China, it's a very big model because it's a socialized government and central planning, and you can mandate things, and you don't have to ask people to share their batteries. It's just they're already all shared. But in the United States, Project Better Place, the one thing that sunk them, and this just blew my mind when I heard this, was compliance. Their business model said, I can get an existing car wash or gas station and put this swap station in the corner of the lot. But it turned out zero, big goose egg of the stations were in compliance on codes and on basically building codes, such that every building that they would try to put this down at would have had to been improved to bring it up to code on the other things they were in violation for. That's what sunk Project Better Place. And it just blew my mind. It was basically people fudging on building codes on why they couldn't actually put it on a shared space. And if they had to build it on a green field, the price went from, they thought they could do it for under $1 million. It turned out to be like 2 to 3 million. And so 2 to 3 million for a swapping station is not the same thing as a video store, right, where you're just swapping videotapes. It was really expensive. Anyway, but that's what killed battery swap in the United States, was code compliance, building codes.
That's interesting. We'll see how it transitions in the future too. But I think the big question is ownership of, how many, I like to think of it too as if, how many people would like to drive their internal combustion vehicle into a station and swap it for, they've got 30,000, swap it for something that has 200,000 miles, on the entire powertrain. There's benefits there and there's ways to get around that, but that's something that needs to be considered. Yeah. So, Ted, thank you very much for the awesome presentation and Q&A session today. Any closing remarks on your end?
Oh, no, just again, if you have any questions, or if you want to join some of these work groups where these slides came from, you can just reach out to me or Kevin, but that's where these slides came from, are all the meetings that we have. And again, it's the unknown relationships on finding someone who, it's much easier if someone finds you than you finding that person. But in these meetings, anything you're looking for, and again, I like the $7.5 billion bipartisan infrastructure law. There's going to be some great opportunities for anybody who's a consultant. And having information like this, gives you a much better idea of what you can write into these proposals for the state agencies that are, looking to spend their part of that $7.5 billion on infrastructure.
Okay, great. Well, thank you very much, Ted. I know there were other questions I saw in the chat. And maybe what we can do is that if they were not addressed, maybe Ted, you can go ahead and answer them through email, and then we can distribute it to the participants, because I want to make sure that people's questions were answered, but we're out of time right now. But if you don't mind, you can answer those, and then through email, and then we can distribute the answers.
Okay.
Okay, great. Well, thank you everyone for attending this evening and for your time. If you haven't already, we have our polling to see what your feedback is about this webinar tonight. So like I said, this webinar was recorded, so you'll receive a copy of this recording, as well as slides that Ted presented. And if you're interested in learning more about what Ted said or joining some of those groups, you can do so as well. And like I said earlier, if you need a professional development hour certificate, we can also provide that too as well. So thank you, Ted. Thank you, Kevin, for moderating. Super, very interesting topic, and a lot of very, very good questions. So I enjoyed it very much this evening, and I hope everybody did too as well. Everyone continue to stay healthy and safe, and we'll let you know when our next VTS Chicago meeting is. So have a good evening, and thank you.
Bye, everybody.
Okay, bye.
Thanks.